Excellent. Now, friends, I want to revisit what Tiffany just said, because it was awesome. Upon doing the second differences up here, her question was, does that always work? Because as human beings, we like patterns, we like repetition, we like predictability. The answer is yes, with a caveat. In perfectly, purely quadratic data, it works beautifully. The trick is, data that you get in reality is never perfectly anything. It's ish. And this is something you need to get used to as you go into the world. For many of you, this is your last math class. I know that. Only a few of you are taking 243, right? A couple of you, yeah. A few, maybe 5 or 6. For the rest of you, this is it. So this is my one chance of kind of doing math with you, but also preparing you for the ugliness and the reality of data that's out there. It's totally cool. Just last class with my 244s, you guys ever heard of touch therapy? It's got a fancy name, but I forget now. But basically the idea is that you can adjust a human's energy field by placing your hands around them and adjusting the energy field and again, it's got supporters, it's got critics. What I did in 244 was I collected some data. Let's see if my students can actually observe that. So I had them sit with their eyes closed, hands up on their legs, and I had students flip coins to decide which leg they were holding a hand over. So a lot of students said, I can't tell. I'm like, just try to feel it. Try to feel whatever this thing is that I can't feel either. Just try to feel it. And then we collected all the data. And what's amazing is the data formed what was almost a perfect bell curve. Almost a perfect bell curve. Almost. It was ish a bell curve. It was ish a bell curve. As a matter of fact, actually, hang on a second. It might still be in here. Let me take a look real quick. Yep, it still is. There it is right there. So, in other words, what you're looking at right here, and this is stuff you'll do in 243 and 244 quite a bit. This is the number of kids that got 0 out of 10 correct, 1 out of 10 correct, 2 out of 10, 3 out of 10, 4 out of 10, 5 out of 10, 6 out of 10, 7 out of 10, 8 out of 10, 9 out of 10, and all 10 correct. Wow. Now when you look at that, it looks like a bell curve, but it's not a perfect bell curve. It's a little heavier on this side than it is on that side. That's, Tiffany, back to your point. Nothing in nature behaves perfectly, but it behaves perfect-ish. Yeah. It behaves close to perfect. And controlling the ish is what statistics is all about. Being able to measure the ish and talk about the ish is what stat is all about. That's what stat is? That's all stat is. It's all about controlling, I shouldn't say control, you can't control anything. It's all about measuring and quantifying how much ish there is. Honestly, that's the lion's share of what 244 is all about.
We should write that in, but, you know, for description.
I wish I could too. I have to call things like standard deviation and all kinds of stuff like that. So anyway, when I look at this data, which is the amount of distance I cover based on a certain amount of time, I don't see a linear relationship. And we didn't see a linear relationship on Thursday because I was going faster as time went on. What I do see, though, is I see a slight curve upward. I see a slight curve upward. There's definitely a hiccup up there at the 100 group. There's a little bit of a hiccup, but again, it's data. It's going to be messy. It's going to be noisy. That's okay. So if I had to pick one of the two models to use at this point, I would pick quadratic. Now the reason we're picking quadratic might, have any of you ever taken a physics class or a GS, I forget which one it is, the GS 105, was 105 physics? You actually study this in that class. When you drop anything on Earth, it accelerates due to gravity. When I roll my bike down that hill, it accelerates due to gravity. And the acceleration is quadratic. I mean, I knew this was going to happen before I started. It was kind of dumb luck that it worked so nicely every time. But I knew this was going to be curving upward as it went. And this again, Lynn, is why we don't need group 175. Yeah. Even not having that point, we can see where that point-ish should be. Right. So what we're going to do right now is, we're going to find the model that is going to best represent the relationship of how much distance I cover on my bike as a function of how much time I'm rolling down the hill. You see what I'm saying there, friends? So basically, we're going to do the exact same thing we did with linear modeling, but we're going to find a quadratic model instead, essentially. The data we'll use, unless you guys have a better idea, and you can, totally. I just figure we'll use this data right here. This is the average of all the groups' responses right here. What we'll do is, let's do this. Let's get some of these numbers down a little bit, a little more. Oops. Let's get them down to maybe, say, 1 decimal. I think that makes the most sense. I don't think. Do you remember how accurate the stopwatches were? Were they 1 or 2 decimals? Do you remember?
2.
Were they 2? Okay, well then we'll do that. We will format the cells so that it has 2 decimal places. Perfect. There's the data we'll play with. So what we'll do is, we'll use these as our x values, and we'll use these as our y values. So the first thing I want you guys to do is to get that stuff entered into our TIs just like you did for linear data. There's not going to be any difference at all in how you enter this data into your TIs or find a scatter plot. Say that again? Oh, just to check. That's totally fine. So take your time right now and enter that data into your TIs. I will do it with you. I will erase this beautiful data from 244. Yes, will I? Will I? I think I will. Oops, not 175, I have 200.
Did you start with 0?
I did. I put 0, 0 in there because essentially that is one more data point. When we said ready, set, go, I was starting at 0 feet at time 0, and then we started counting from there.
Do we not include
the 175?
Yeah.
We don't have a data point for it, so we just jump over. And it's okay.
You put
It's
0?
okay. All Excel did, if you remember, all Excel did was it skipped over that data point. Now I can't see it. Hang on. It just left a blank there, and your scatter plot will too. So once you guys get your data in, make a scatter plot using your TI. Just use your little booklet. At this point, you're in your booklet that I gave you last week, exactly the same. You're doing nothing at all different except going X's and Y's. So X is going to be time in seconds. X is going to be time in seconds. And Y is going to be distance covered in feet. Distance traveled in feet. Turn this off for just a sec, because what I want to play with real quick, insert, equals this, minus this, drag that down. Get rid of this one. Yeah, messy. Do we have the data in?
No, just about almost really close.
I was just saying, can I turn the projector off? Can I turn this off?
Oh.
That's the one downside is the recording always looks better when we're looking directly at the front board. So I was kind of want to, once we have all the data in. Well, I'll tell you what, let's just do this. I'll put mine up there so you can see mine. Oops, turn this off. Get that in slightly better focus. And I want to clear this board so you can use it to do some more crunching. There, don't need this. We'll need the space. So what I really want to know is I want to know how fast I was going as soon as I crossed that last time marker. That's what I really want to know. Is I want to know how fast I was going when I crossed that last time marker. All right. It's a little slightly bit out of focus. I apologize, friends. We can live with that, I think. All right, did you get a scatter plot? Let's get caught up with you guys. Turn that off. Scatter plot on. Just like this, L1, L2. Yep. You're doing this the same way you did for linear data. Exactly the same. L1, L2, scatter plot. Yeah, Tiffany, what's up?
Why is it stuck over there? It's not doing something right.
Well, just are you following along in your little booklet?
Yeah.
Where's it giving you the issue?
When I went to press graph, it just says error.
Don't press graph, press zoom 9.
Oh.
Zoom 9, which gets you, look at that. Look familiar?
I had to take my equation out. I had an equation in. That's what happened to mine.
And if you remember in your booklet, it tells you to do that too.
Yep. Screwed up.
I tried to make that booklet as error free as possible. So basically, I mean, I've got an equation in mind, but you just don't see it. It's off this screen. I can turn it off though, and clear it out if you guys want to. So we getting some success with that? We getting some success? We got ourselves a scatter plot. There is a point down here. It's kind of hard to see. He's right over here. That's 0, 0. This is the amount of time it took me to get to 25 feet. Now at this point, and this is purely if you want to start finagling, I'm going to go over to window, and I'm going to change, you see that Y scale? For whatever reason, it's set to be 0.1. I'm going to make it 25. Because on that Y-axis, you guys were set 25 feet apart from each other. So now when I press graph, I see a dot at each of those 25-foot increments. Does that kind of make sense? Ish makes sense.
Enter after that when we change the Y scale.
Graph.
I'm sorry, could you go back to the window?
Yeah.
Sorry.
Window, and then just I changed the Y scale to 25,
Yeah,
Y scale.
that's what I'm asking.
and then just press graph.
Oh, okay, good.
You can press enter, but you don't need to. Yeah, Tiffany. That means your data is not right.
I got
That means you don't have the data
done.
correct. Right, just in case you see it. So, you're missing 200. No, the 175 time. We don't have it. We need 200 times. So, friends, what was the time on 200? 200 feet? The last time for 200 feet? 10 something. 10.34. There you go. Now it's going to behave this way. Now, at this point, we've done nothing new. This is exactly what we did for linear regression. But now we don't want a linear regression, we want a quadratic regression. I should be looking at this, make sure you can actually see this-ish. Okay? So, go back as if you were going to get a linear regression. So, stat, calc. Now this is where we lived before. We went down to linreg ax plus b. And if you run linreg ax plus b, it'll give you an answer. Don't do this. But watch, it'll do it for you. Oops. It'll do it. Watch this. Okay? If you stick it in y1 too. It'll do it. It'll say that's the best fit line. And there's the best fit line. The problem is that line does a crappy job of talking about what's actually going on. It totally misses the point that I'm getting faster as I spend more time on the bike going downhill. So it overestimates in the beginning and underestimates at the end. So, although it will find you a best fit line, this is why I make you make a scatter plot. So you look at the data and go, oh, look at that, it's curved. It's curved like a parabola. So now we go back to stat, calc, and we go one below, which is quadratic. Quadratic, number 5. You still want to put that y1 on there. You still want to put that y1 on there. Okay? So vars, y1, just like that.
Wait,
So
do that.
look at your booklet, top of page 3, top of page, everything is in your booklet, friends, except for quadratic. That's the only thing that's not in your booklet. In your booklet, it's linreg. Everything else is exactly the same, hence my gift to you of the booklet. Yes?
I have a question. Why yours just shows A and B?
Yes.
Mine's showing C and
Brother,
R squared.
that's because I did linreg, not a quadratic. Watch this.
Oh,
There's your C.
okay.
Now,
Where's the R
don't
squared?
hold that thought. Hold that thought. Okay. Now, notice the difference in linreg versus quadratic. Linreg had ax plus b up top. That's because that's what a linear equation has, is a slope and a y-intercept. A quadratic equation like this one has This guy out here, which is the acceleration, which is, if you will, the slope. This guy, the linear coefficient B, and this guy, the y-intercept, which is now called C. So we should all have those three values now. So the equation that actually governs what I'm traveling is going to be the distance I travel in feet is equal to, we can round these off to one decimal, 1.5 x squared plus 4.4x. And this is a minus 1.9. That's the generator for the amount of distance I cover on my bike with respect to how long I've been rolling down the hill. Press graph, and you'll see it in action. And you'll see how that curve actually picks up the data. You see that? Remember how the line pretty much completely wrongly estimated? The parabola actually picks the data up and says, oh yeah, it's actually adjusting it for that force of gravity. You're going faster. In other words, you're covering more distance the longer you go on the bike. You're covering more distance the longer you go on the bike. Is that, go ahead.
I missed the part of getting the line on there.
Just press graph and it shows up.
Ah, thank you.
There you go. Yeah, but friends, that book that I gave you last week, everything we just did is in it except for what? Picking quad reg versus lin reg. If you want to, write that in that step where it picks the lin reg, just write in 5 quad regs. That way you know where it is. And next week we'll do X reg, which is another choice. But everything's the same. Clearing the lists, getting the data in, all of it's the same. It's all identical. It's all identical. Okay? Now, what you're looking at, you can turn your scatter plot off now if you want to. You can turn your scatter plot off now and just look at the curve if you want to. So the easiest way to do that, is to go up in the y equals screen, press enter, which turns on plot 1, which turns off plot 1, and then press graph again. There's my position curve. It's how far I've gone down the hill, corresponding to how much time I've been on the bike going down the hill. How far I've gone down the hill, which is on the y, with respect to how long I've been on the bike going down the hill. It's a position curve. Stop right now, make sure we all have this curve in our TIs. We got success, we got the thing. No, what's happening? What error is it giving you?
Nothing, it's just not putting the line up, so I...
You didn't put Y1 in.
Oh.
So make sure you get Y1, dim mismatch. Read the error on the back page right there about how to deal with him. Friends, that booklet has everything you need to know in it. If you're going exactly through it, it will give you exactly what you've got. Please. Say that again?
Quad reg one, the last step that's not in the booklet.
Oh, where it says lin reg, do quad reg. That's it. See where it says 4 lin reg in the booklet? Where it says 4 lin reg, just change that to quad reg. That's the only difference, 5 quad reg. Yep, there's nothing, the reason I say this is there's nothing to show, it's just a matter of grabbing 5 versus 4. Yeah?
So once you get into the quad reg,
Yes?
it pulls up X list L1 and Y.
Oh, wait a minute, let me turn that off. That's a bug that I have to change. Yeah. Cool? Alright. Is anybody else's TI 84 not behaving? And when I say not behaving, is it when you type quad reg, does it give you a very strange screen? I can fix that. I think I fixed them all now. I fixed a few last week. I think I fixed them all now. 83 should not be misbehaving, though. They should be working just fine. Okay. 83s don't have the issue. 84s sometimes do. Okay, friends. Now the question I want to ask is, how fast was I going when I passed the 200-foot group? That's the question that we're going to leave up, and it's going to take us about 30 minutes to answer it, because we have to build a skill set. We already have one skill set. Why are these lights off? We already have one skill set. The one skill set is getting the data into the TI and getting that equation. And that's a great equation. It's a fantastic equation. The problem is, what we need a way to measure that based off of this new construct that we have. And in order to answer how to do that, we have to introduce the idea of average rate of change. Average rate of change. I'm going to sometimes shorthand this as AROC, for average rate of change. You guys probably know it better as speed, or how fast you're going. For example, if you had to guess how fast I was going on that bike when I went by the 200 group, give me some guesses.
11.
11 what?
11.7.
11.7 what?
Miles per hour.
Miles per hour, or maybe, I heard second, so what would, how fast was I going?
Oh,
Feet per second, miles per hour, kilometers per hour, miles per minute. Every unit, whatever unit you choose to give me, is a distance per a time. That's what speed is, right? Right now it's snowing at approximately 1 inch per 4 hours. We'll throw that out there. Yesterday, if you were in class around 10:15 to noon, it snowed at the rate of 2 inches per 2 hours, or 1 inch per hour. Because when I went into class, there was no snow on the ground. I came out 2 hours later, there were 2 inches of snow on the ground. Therefore, it snowed 2 inches in 2 hours. These are rates. Any kind of a rate is going to have some kind of a metric divided by some kind of time. That's what speed is. It's some kind of, I'm going to generalize this to our bike speed. It's some kind of length over some kind of time. Well, that looks like a slope, doesn't it? That looks like a slope. It's a change in length over a change in time. And guess what? It is a slope. Look at our graph again, friends. Now, I know the TIs have crappy graphs. What are the units on this horizontal axis? What quantity is being measured down here? Time. Time in seconds. Well, no, how we set it up. We set it up to have time down. We could, yes, absolutely. We could turn it around and make time be up on the vertical. But because I want to keep it with how your minds process rates, we'll put time down there.
no, I was just talking about the time. It could be seconds, hours, minutes.
Oh,
days,
yes,
years.
exactly. But we did it in seconds, so I want to keep it in seconds. What's on the vertical, friends? Distance in? This up here is distance in feet. So you see, we have the units set up for speed. We've got feet per second. We've got feet per second. You guys buying this? You buying this logic? Please. Matt.
Yeah.
Matt, go ahead.
This is a little off topic.
Go ahead.
But, so like, say like at the mountain, like when they're building like jumps.
Okay.
So like if you were to have like so much slope coming down the mountain and you were to put a parabola curve there for the lip of the
Which
jump.
I think they do. I'm pretty sure they try to cut those in there, make it
Yeah.
smooth.
So is that how they figure that out? Like to have a landing over here, how would they? I'm
You'd
just
have to.
wondering.
I don't know the answer to that, but here's one thing I have a related issue. When I built my shed on my property, I built it right up. I broke code on this. I didn't realize till after the fact. But I built it as close as I could to my neighbor's fence, so that when the water, when it rained heavily, running off the roof wouldn't go into his yard.
Okay.
So essentially, the water comes down at a linear, and then as soon as it leaves the roof, it falls off at a quadratic.
Yeah.
And I did the math on it, and I figured out if it's any more than 1 foot away from the fence, the water's going to go into his yard and probably piss him off.
Yeah.
Now, code says it has to be like 3 feet away, but I totally ignored that because I didn't know about it until it was after it was built anyway. So I'm guessing that the same thing happens. They figure out there's a mathematical and physical relationship. When you come in at a certain force, you're going to leave the lip of that.
Yeah.
And worst case scenario, if you leave it so that you're going that
Because
way.
if you think about it, you're doing kind of a reverse curve when you go.
Well, you're doing
up.
both.
Yeah.
You're following but there's forces involved too, not just position.
Okay.
See, we're not measuring force here.
Okay.
We're measuring just my position on the hill. So in other words, we're not measuring, say, my momentum that I'm generating. So there's another physical argument that this goes over and above. Great question, though.
Okay.
It's a fantastic question. It's beyond, it becomes a physics.
Because we were building bike jumps the other day with my buddy, and I was like thinking about it because he's like a BMX rider, and we were building these giant lips and a landing, and I was like, dude, how do you know?
So much of that is
thinking
feel
in
for
your
those
head,
guys.
you know? Like,
Because they can control where they go as they leave the lip.
Yeah.
If they pull back, if they push forward. I mean,
Yeah.
so much of that is,
It's-
what you're asking is, suppose you take a perfect sphere and let it roll into that, where's it gonna go?
Yeah.
But those guys and girls that do these tricks on snowboards and skis and bikes, they're controlling their
Yeah.
exits in a lot of ways.
Totally.
So there's many more variables at stake than just the pure. What I tried to do with this experiment was break it down to just gravity. Gravity pulling me down the hill. I didn't want to pedal. I tried to stay consistently goofy looking on the bike. I mean, I was trying to make everything as consistent as possible.
Yeah.
Great question.
Yeah.
But there's so many variables that we
Okay.
can't graph it with just two anymore.
All right.
But the basic idea of what we're talking about here ties directly into that.
Okay.
Is that fair?
Yeah.
It's a roundabout answer to your question, but we can't
that's
answer your
fine.
question well as we can answer this one.
All right. That's cool. I was just wondering.
No, it's fantastic. It's fantastic. Now, I just mentioned yesterday when it was snowing, as it's snowing even heavier now. Yesterday, I went into my 10 o'clock class, no snow on the ground. Came out 2 hours later, 2 inches of snow on the ground. Which means the rate of snow yesterday was 2 inches per 2 hours. Or